Good afternoon, everyone in India. Good evening if you're joining from other parts. Well, if you're joining from further east of India, and welcome to our Robotics Cafe. So, pleased to introduce Dr. Juxi Leitner. He's an applied science manager at Amazon in Berlin, Germany. He has spent the better part of the last 2 decades conducting robotics research across academia, government, and industry, and most recently as senior lecturer at Monash University in Melbourne. Before joining Amazon, Juxi was founder and the chief technology officer at Leitner Robotics. It's an Australian venture capitalist based startup. I'm sorry, and it creates general purpose pick and place robots and the software to deploy them in the food supply chain. In 2017, his team from the Australian Center for Robotics Vision won the Amazon Robotics Challenge. So, Yuxi, it's great to have you here. Over to you. And folks, if you have a question in the middle of the presentation, so just check with Yuxi and you can just raise your hands if Yuxi is okay with it. Or better still, just keep your questions for the Q&A session at the end.
Yeah,
Right.
cool. Awesome. Thanks for the great introduction, Aditya. And thanks for the invite. I'm by training a lecturer, so yes, I can lecture, but again, feel free to ask questions. And yeah, Aditya, let me know when we're getting close to the time as well. So I'm not blabbing on for too long. Yeah, so again, thanks for the invite. I'm gonna give a bit of a talk that's maybe not super technical, although there's some technical stuff in there, and more about some of the different perceptions and different angles that you look at more or less the same problem when you come from an academic startup or industry point of view. And as mentioned, I was with Monash University. I'm still an adjunct at Monash University, but I've since moved to Berlin in the last couple of months. And I'm actually right now back in Australia. So I'm further east than India, so it's evening here. I'm really happy to talk about what I've done. This is more from like a different presentation, but like there's your more traditional academic career pathway, do your master's, your PhD, and then go into academia, do your postdoc, and become a lecturer, and so forth. These days, a lot of times people have different and diverse backgrounds. I think I have lots of different things that I've done, and I guess this is not to show off all the things that I've done. This is more like for the people that are on the call. You don't always need to have a plan, right? I didn't have a plan of what I wanted to do all the time. I just ended up saying yes to a lot of things and did some cool things, but I didn't have a nominal plan to stay in industry or stay in academia. I always just like talking to people, understanding what the different things are that are going on. And so I guess the common thread for me is I'm kind of fascinated with manipulation, like dexterous manipulation that we do with our hands, but also how we get robotic systems to interact with the world safely and in a reliable, useful way. I'm very fond of the movie WALL-E, so most of my presentation have at least one WALL-E picture in there. Here's the WALL-E picture for this. I really think it's a really nice representation of what we want our robotic systems to have, right? So be curious about the world and interact safely and perform useful tasks. On the left-hand side, you see one of my PhD projects when I was doing my PhD in Switzerland. This is a European humanoid called the iCub, and that's been around for a while. And if you look very closely, it doesn't have legs. So we only work with the upper body humanoid. And in particular, my research was on how to make that upper body humanoid actually picking up things, particularly picking up things that potentially are not static. So you can see my hand in there, and I'm trying to move like this blue cup up and down and out of the way of the robot. And the robot should try to like pick this up. And we were very excited about this about 10 years ago and what we can do with the humanoid. Obviously, there's a hype about these things now, but like for me, like trying to get robotic systems to pick up things has been going on for a long time. But actually, picking up things is most of the times quite a different thing if you're looking at different scenarios of that. On the left, you see a drawer, and very often when we talk about dexterous manipulation in academia, we think about something like this, a scenario where there's lots of different items randomly placed in a pile or clutter, and we try to pick them up. The middle part, I swear it's not my bedroom and my cupboard, but this is like sort of the things that some of these startups right now are talking about from a humanoid robotics point of view. The environments that they want to work in and the environments that they feel comfortable sending humanoid robots in. And on the top right, this is the world that I live in at Amazon. I go a bit more into details in a couple of slides. And the bottom right is the world that our startup lived in, Lyra, when we were picking up fresh produce. All of them are robustness or driven by robustness, but they come from a different angle. And what I'm trying to do today, in the next half hour or so, is trying to see how robustness differs if you look at it from these different angles and different scenarios. I assume that most of you will be from academia. And so let's start with the academic point of view first. So I've been working on robotic manipulation, as I said, for a while, and as also at a TTSN in the intro for a long time. I feel old when he said that, but yeah, this is work that we did in the mid 2010s. So that's 2016 to 18. We worked on how we can get a robotic system to be robust to changes in the environment. So picking up items that are moving around, picking up items that we might have not seen before, picking up items that are in a pile or in clutter. And if I start moving on one end, the other parts fall over. All this is sort of under the umbrella of what we call reactive grasping. And particularly at that time, we still looked at tabletop grasping, meaning that you have a table or a desk where things are placed and you're coming from the top, and usually you have an overhead camera looking down and you're trying to perform a grasp. Don't worry too much about technical details here, but like this was the 2010, so everybody was doing deep learning, and so did we. So one way for us to deal with how can we become more reliable and robust to these changes is by adding this reactiveness. We were in a research lab that did a lot of work on visual servoing, and inspired by this, we had a neural network that we could train grasp poses for. And what you can see here is a robot arm, industrial type robot arm. It's a Kinova arm from Canada, with a 2-finger pinch grasper and a wrist camera mounted with this 3D printed red block there. And we're trying to pick items that are moving. And what you can see is that actually we have in the control loop this visual detection of what is a good grasp point. And again, I can go about the details later in the Q&A. But the point was more, we could show that this reactivity allows us to pick up from not just the clutter, pick the most pertinent item, but also while this clutter is moving. And we could show that we could empty a table with lots of random items on it. And so this was our approach to robustness and how we thought about, this is a way of creating a robust grasping stack in academia. Now, the problem in academia is we would like to benchmark each other's work, right, and try to trade things off. But it's actually not that easy to say, my clutter versus your clutter. If you look at that video here again, like the clutter, it's just a bunch of random items. Like literally most of the time, it's items that you find in your robotics lab. So I think there was like some plush toys and plastic banana and like some yarn and a ball, literally things that you find, right? But it's really hard to compare that to somebody else's algorithm. And so one of the things that we try to do is, can we somewhat standardize that? And we were not the first ones to do that. There's lots of different ways of benchmarking grasping out there. But what Doug, one of my PhD students at the time, did was, can we find a more optimal way of a distribution of items? And he called them EGAD, which is an evolved like evolutionary computation. It's still a thing. An evolved data set of different items that provide a grasp difficulty, so like from simple to complex, and a shape complexity from like more spherical round to like really spiky, pointy things. And by having this, we could show that we actually would be able to cover a large scale of that 2 axes that we have here as a plane, compared to some of the other standard benchmarks, so DexNet and YCP are other benchmarks. And for us, that is a means for showing robustness of the algorithms by having a large scale of items that we wanted to pick up and providing that as an input to the system and as a comparison between the different data sets. So I think that's a very common way in academia to think of, like, how do we compare? We create a metric and we create a benchmark and we try to compare things. As I said, a benchmark is usually not just items, but like actually a task that you perform. So we actually came up with a different way of how we could define tasks that are not just tabletop. Again, like expanding on the robustness idea, like, we claimed that our system can pick up everything, but from the top. Can we now pick up everything, but like from a front on shelf? And what we decided to do was use an IKEA shelf that is commonly available and items that were commonly available from that YCP data set before. And by not just providing a set of items and a specific scenario of like a physical representation, also physical placement. And so we printed these stencils on the top right here that you could place into the shelf. And then you could say, place this item at this position and maybe, at 2 points. So you could actually play around with the orientation as well. And therefore would allow people on different parts of the planet to compare a specific task where you say, like, there's now 5 items in this shelf and you're trying to pick up one item, but it becomes a lot more comparable. And therefore, ideally, you could show that you could actually make progress on robustness. Well, the other interesting thing is, in academia, we very often define the metrics that we're aiming for as well. But it turns out, particularly for grasping and manipulation even more so, we actually are not, as a community of robotics researchers, we are not actually aligned on what a good metric is to define how successful grasp points and grasp tasks are. These are two papers that I randomly picked. I'm a co-author on both of these papers. That's why I picked them, just to show that even within myself, I'm sometimes not clear what the best metric is. And that's a very common thing in academia, right? We change the metric as well as the algorithms because we are ideally making progress. And when we make that progress, we are looking at what the next target is to showcase a more capable, in this case, manipulation system. But that's a very common thing. One less common thing, but also that happens in academia, is that usually it's student-driven. We have these challenges in competition. So this was the Amazon Robotics Challenge in 2017, and Aditya mentioned it already in the introduction. We won it with the team that we entered. But for me, it was a way of showing that the technology that we built in sort of isolation, a grasp stack, a perception stack, could actually be integrated into a system that can perform tasks. And in this case, it was very similar to the shelf benchmark that I just mentioned before. It was a benchmark on how to pick up things in a shelf-like scenario. It was sponsored by Amazon. It was like 32 teams in the world and 16 made it to the finals. And we outcompeted the other 15 to win the challenge. And the top part is more like how we actually pitched this to investors. But again, I think the robustness aspect grew, right? Like all of a sudden, you're not just like picking up random items that you select, but part of the challenge was Amazon is giving you 42 items. And in fact, on the day of the challenge, they will swap 50% of these items to new items, and you only have 1 hour to prepare for those new items, which is much more closely aligned to how it happens in industry and particularly in Amazon right now, rather than in academia where we define the items, where we define the benchmarks, and we define the metrics upfront so we can actually do these things. And this is a slide from 2017, so it's basically just copy and paste from back then. But for me personally, it will also transition into a startup because the capabilities that we showed in this challenge, for me personally, showed that we had now the capabilities of not just an algorithm or a slither of technology, but we had a technology that would actually potentially make a really interesting product. And so we started thinking about like how we would turn this from an idea and theoretical algorithmic breakthrough into something that is a product. And this is a slide from 2022 when we pitched to investors as Leitner Robotics, which is an Australian startup, as mentioned before. It's still existing. I'm not actively involved in it anymore, but I was one of the co-founders in 2019 of the company. And one of the focus areas of this technology and this product particularly was fresh produce sector. Australia is a very large producer of fresh produce, but labor and particularly labor availability is a constant crunch point, particularly in the remote areas of Australia. But on the other hand, it also deals with a lot of complexities. This one is packing zucchinis on the left, and the same robot is actually packing avocados on the right in the picture there. This is a slide from when we pitch to investors, and you always have to kind of like upsell it. But again, very similar to what we just said in the paper before, a couple of years before, here to investors, we said we have a robotic system that's robust enough to pick up a lot of different fresh produce and protein items. And particularly, we try to understand how we can build a product out of it. But actually, very quickly talking to customers, turns out that they are not really caring about the metric of your wonderful convolutional neural network. For them, the product is not the robotic system and it's not AI. For them, the product is a thing that provides, in this case, a service or pack produce items into a box. So I think this is a lesson learned from doing this tech transfer and trying to look at it from like that different angle. The robustness is not about the specific robustness or capability of an algorithm, but like it's the robustness of the whole system. How many people do you need to stand next to a robot to fix it when it breaks? How often does it break? And what is the robustness, particularly if, let's say, you want to pack zucchinis in the morning and avocados in the afternoon, and maybe the next day you want to pack sweet potatoes. And this is all things that we try to do with our robotic system. The other thing, and this is again a slide from a couple of years ago from our startup, where on the left-hand side you see a very early prototype of our system, also in a warehouse-like scenario. And the BHAG is an venture capital acronym. Stands for Big, Hairy, Audacious Goal. So it's basically what is your main goal that you try to achieve with raising funds. And for us, reliability and robustness, not on this slide, but like under the larger umbrella, was one of the things that we wanted to aim for. And that was coming out of a conversation with the customers where, you need to pick millions of items per week. Ideally, you want to pick a range of items, so something that's a couple of grams to something that's really heavy. Like I think the heaviest thing we picked was a watermelon of like about 5 kilos. But you also need to be able to make this system robust and reliable enough that like even if you change the box type, you can actually pack that in. And why is that actually important? Because turns out that these boxes are not exactly always the same. They come from different suppliers and there's margins and variations in there, but they also deform, particularly if you're in humid climate in the very north of Australia versus in the south where you might have a very dry climate. These boxes actually shift around and deform a bit. And so you need to be able to be robust to those changes. So that was the pitch there. But turns out most of the investors didn't really understand what intelligent robots are. So this is a slide. Again, I'm rephrasing what it is that we as academics would say is a robust system or a robust algorithm to something that is a robust product. And then in simple terms to investors, explain what that means. Also to customers, right? Like, as I said, most of the time customers are not interested in like the underlying technology, but they're interested in the capability. And so one thing that for us was a core part to making it intelligent and why it was needed in the scenario is packing zucchinis here. We have a sensing system, in this case, a camera that looks down. And why is it important? Because as you can see, new produce is rolling in at random times. Even if you pick up one piece of zucchini, the other ones will slide in. So we need continuous information from the sensing capability to be robust to those changes, right? Like none of these zucchinis are identical. They wobble around, they roll around. And so you need to have a sensing capability that is robust. At the same time, we need to be flexible enough and adapt if things go not according to plan. So on the very left, you see us placing a zucchini, and because the zucchini is not totally straight, it wobbles around. And if you have like just a fixed pattern, because the farmer tells you there need to be 6 zucchinis on the left-hand side and 6 zucchinis on the right-hand side, if you would just blindly put the 4th zucchini in where the 3rd one now wobbled to, because that's the place for the 4th one, you would not create a robust system, right? All of a sudden, the capability of your system would not be working all the time or every day, or even just like for an hour, because these things keep happening all the time. So this was the other part that we sold to customers. We are actually able to adapt. Again, we do require the sensing, but then we require the smarts to understand what the state of, in this case, the box in the world is. So we can be robust to some of these changes when they happen. And the third part, we need to also be able to recover. And this is actually something that's, I personally feel, particularly in robotic manipulation, maybe a least or sort of like less research topic in academia is like, how do we do error detection and error recovery, or even just failure detection? I think is a very important part, and it's a really critical part for startup and also for industry. And I have another slide on that later. But what you can see here is we're trying to pick up the same zucchini many, many times. So it's the 3rd or 4th one from the left on the top there. The 3rd one, we try to pick it up. We can't do it. So pick another one. We try to pick it up again. Can't do it. So we pick another one. We pick another one. We try it again. We can't do it. Pick another one. We try it again. Can't do it. Pick another one. And eventually we actually pick this up, right? So I think this is an important display of robustness, particularly against the customer. What most customers hate is that the robot just repeatedly does the same thing and it doesn't work, right? Like, if your optimization always gives you the same, or your ranking of grasp poses at any point, always gives you the same grasp point, but nothing has changed, you will not succeed again, right? And this is not just a capability question, but it's also throughput and in the end, an ROI question for a customer. So it is actually critically important to understand whether you are successful or not. In some cases, actually much more important than making it even better at the job. As long as you're somewhat okay, but you also know when you are failing, I think that's a really good entry point for like a product into the market. And so that's sort of more from the startup angle where you're selling both to the customer, but also you're selling to investor, because you're always kind of just half a step ahead, right? You haven't fully developed the technology, but you have a path towards it, while at the same time you're trying to convince investors to put more money in to help you with generating that technology that will create the product that you need. And third and more recent one, I'll talk a bit about how the challenges in industry are looking like, and particularly at at a scale of Amazon. And these are slides from Amazon from different presentations, a bit merged together. As mentioned before, I'm with Amazon Robotics, and particularly with the Berlin office in Germany, where we have now a team of probably somewhere between 80 and 100 people. It keeps changing on a daily basis because we are hiring. But it's a team that's specifically in a project which is called Vulkan. And you can Google that. You can find a lot of information out there about it. But particularly in Germany, we are having a product called Vulkan Pick. But we have a sister team in Seattle called Vulkan Stow. And both of them, we are trying to pick from these shelves that you can see in the back there. And we call them fabric pods. So they're cloth-based pods, meaning they're very deformable and they have very, very many items in there. And they have some very interesting challenges. But why, for me as an academic going into industry, like why do you want to work with Amazon? Amazon has a long history of deploying robotic systems and is probably one of the largest deployers of robotic systems in the world. So there's more than 1 million robots deployed in Amazon globally. Most of them are in what's called fulfillment centers, which is basically an Amazon term for warehouse. But most of them are these blue or orange robots that move things around, in this case, shelves. But very few of them are robot arms. And I think there's a few reasons for that. But in particular, what we are doing in Amazon Berlin is to deploy more robotic arm systems to perform tasks. And these tasks, there's a couple of videos that I grabbed off Instagram and other things. You can see those yellow pods look like they are driving themselves, but they are being driven by these robotic systems underneath it. And people putting items in there. So you see a lady there on the left putting in a rather large item into the bin and somewhat struggling to get it in there. What you can also see, there's these elastic bands around the bins. They're there because when these shelves move around, you don't want items to fall out because there's no people in there where the robots move around to pick it up, and you don't want other robots to drive into them. So there's these elastic bands, and you can see how the person needs to actually push the elastic bands aside to put the items in there. And as I said, this is a stowing side. It's been done in Seattle, trying to automate that one. We are trying to automate pick in Berlin, and you can see two people picking there on the right-hand side. And they are, these shelves are a bit more than 2 meters tall. So sometimes people have to bend over to reach the bottom rows, and sometimes there are those stairs that you can see in the middle video there on the left. They use those stairs to actually climb up to reach into the top shelves. And so you can also see that sometimes people are struggling to pick the right item. So there was 2 items that looked very much the same, and you had to go in and actually pick up the item. So these are the challenges that Amazon is facing. But actually, if you look at what happens once you click the button of like, I want to order like a Wally DVD and a pair of socks or whatever it is that you want to order, we are only a tiny fraction and one step in many that actually fulfills an order to you. So between, inventory arrives and being stowed in these massive floors. So this is a video where a drone flew one of the fulfillment centers. And you can see there's a near endless amount of shelves in there. And there's millions of these yellow shelves in the world. And so these items are being stowed once they arrive, right? Like, so inventory arrives and we put them in the shelves and then people can order them online. And once people do order them, people need to pick that out. But that's not where it ends, right? So it's a very, there's very many steps in a sequence, and most of these steps are in parallel. So you can actually perform multiple millions of these things in parallel because there's millions of orders coming through that need to be fulfilled, right? So the scale is pretty large, but also just to understand, like, we are only a tiny part of this problem that we're trying to solve, right? Nevertheless, it's a quite interesting problem of scale. There's hundreds of warehouses, there's thousands of robots that we, are in the, aiming to deploy. There's thousands of humans in each of these warehouses performing some of these tasks. There's actually some of the robotic system that not our team, but other teams have deployed that pack parcels. And I think you can Google that. There's other projects that have, sorted a billion parcels in Amazon fulfillment operations. And there's lots and lots of possible items. So I've heard, large numbers of millions of items being in a single fulfillment center. Here it says like 100 millions of possible items that actually come through, and they keep changing. And Amazon packs 10 million packages per day, right? So like it's a massive operation. And that comes both, with the challenge of like how do you deal with these large numbers, but also with the opportunity, right? Like if you can only make a tiny improvement, tiny part of the problem, you're actually making these systems a lot more efficient to get things out to the customer. This is more like a corporate slide, so I'm going to go quickly over it because computer vision is not a new robotic sense. We've worked on this for a long time for Amazon. I think deploying them on these robot arms is new because like a lot of the drive units do not have it. And yeah, like, I think most of the people in the call will hopefully know that computer vision is a sense that robots have used for a long time. But so this is a picture actually of our system. So you can see the same yellow shelves being driven, in this case, by like one of these orange drive units to our station. And you can actually see that we have multiple robot arms that we require to perform the task. We, and particularly the team that I coordinate, which is called the extraction team within Vulcan Pick, we are dealing with like extracting, as the name suggests, the item out of the bin. And so what that means is we actually have one robot arm that just opens these, elastic bands that I mentioned before, and the second robot arm that actually drags the item out. During that operation, that conveyor belt is actually moving up, and we just drag it out of the shelf onto the conveyor belt, and then that yellow shelf can already move away and the next one can arrive, right? And after us, somebody's dealing with the item after it came onto the conveyor belt. And that's the way of parallelizing the process so we can actually process a large number of systems. But you can also see that these are stationary robot arms, unlike some of these pedestals here. There's lots of cabling, there's like grass pack, there's like conveyor belts, there's a complex systems engineering problem, as well as just a science problem. I've hinted at this before, right? So this is what we actually see. And one of the nice things, so I'm an applied science mentor, I'm meant to actually bring in science into the product. And one of the nice things and one of the reasons that I'm excited about this is the whole world for us as Amazon manipulation, as Amazon pick in this particular case, is that it's a couple of inches by a couple of inches of a bin, and they're all a couple of inches deep. So it's a very small world. We don't need to solve the whole self-driving car. Everything needs to work everywhere on the planet, or domestic robots where every household will be completely different. We have a very small world, but in that world, there's lots of things happening, right? So and I know you can unmute yourself or put it in the chat, but like, can somebody tell me how many items are in this bin here on the bottom left? Guesses are totally fine. 6, 5, 5 to 6, 9. Cool. We can try to get a distribution. I haven't counted them, but what you can also see is it's actually really hard to understand what is in the bin before you open the band, right? So you actually need to open the band to understand what's going on in the bin. The problem though is sometimes things already start like lean against the band, and when we open it, they might fall out, which is not ideal. The other problem is when we try to open this bands, we might accidentally destroy some of the items behind it because we have a finger that we sort of like try to get in there. So you can see some of the challenge that we have. And we've done some work on like, starting with a heuristic and a sort of good old fashioned engineering approach to try to solve this. And over time, added more and more machine learning, more prediction, better ways of reasoning. And that's reasoning, I guess, in air quotes. So we can actually assess the risk of what happens when we open that. And so, again, I'm not going to go too much into the details, but like we need to figure out where in this plane we need to stick our finger in and how we need to open that. And so this is a prototype from a couple of years ago. We actually, and I wasn't there at the time, so when I say we, that's the royal we in this case, where they tested different end effectors, they tested different vision systems just to see whether that's feasible, right? Like to get these projects going, even at Amazon, and probably even more so at Amazon, you need to showcase that you have all the capabilities in place so you can actually perform that, right? Like it's not a complete moonshot. Yes, sure, at the beginning it is, but then you like work through it and say, well, can we pick from clutter? Can we deal with those bends? Can we deal with like that wobbly shelf? And you want to showcase all these capabilities before you start building the system. So this is just the robotic system trying to open these bends. personally, I find it really fascinating because elastic bands are super tricky. The perception is super hard because these things don't reflect very well, so like your depth is very much out. So you kind of visually need to estimate where things are. But we actually made it to a point where this is becoming very, very reliable. And again, it needs to be robust to changes because there's millions of these shelves out there. All of them have been interacted with a different amount of time, and some of these bands are very stretched out. Some of these bands are very fresh. So the forces and how you interact with these bands are actually varying quite a bit between different interactions. And this is the robustness that we now care about. How can we actually deal with that part? The other part that we need to be robust to is we'd like to get an item out, but like sometimes an item is blocked by another item. And so this is actually not trivial. Like sometimes there's two things that are stuck in very close to each other. And so we started using policy learning and reinforcement learning to learn policies that will allow us to drag an item out, even if there's occlusions, even if one might be covered by something, or there is a lot of interaction potentially going on. And the really interesting thing is to make that robust, we actually don't care about what the item is. We care about like the interaction between the items a lot more. So we actually work in depth rather than RGB because it's a geometric problem much more than an item ID problem. And so that actually allows us to work in a simplified simulator, which we can transfer to the real world. And you've seen that here in the video where we're trying to make that happen. And again, this is aiming at like being robust to like these millions and millions of items that we actually interact with and get to see. But then actually to extract the item, we need to do a bunch of different things as well. We need to, first of all, understand how many items are in the bin. And this is sort of where we start. We segment the items out. And then we need to understand, well, which one of these segments is actually the item that I want to pick. If you pick up a, blue toothbrush rather than a red toothbrush, people will be slightly unhappy, but it's probably not a big issue. But if you pick up, um, Samsung instead of an iPhone, people will care that you sent them the wrong item, right? So part of the problem is like, how do we deal with that? But there's a lot of different, item ID questions, so identification questions that need to happen before we even get to the point of pick post generation, right? Like we first need to understand which part is the right item, potentially then do some 3D matching or shape completion before we can figure out what are good pick poses. And again, the very first slide was the picking, tabletop downwards facing camera. Now here we have a camera at an angle going into a bin, and we still need to pick it out. And the noise is somewhat tricky there as well because there's lots of potential reflections or different items in there. And then on the way out, we actually want to make sure, well, actually both on the way in, when we extend the suction cup, but also on the way out when we get the suction cup back out, we want to make sure that we actually have attached ourselves to the right item and we drag the right item out. So we can do very simple 2D or 3D tracking. And again, you can start these things with like good old fashioned engineering before you need to get relatively complex. Another interesting thing is we need to, and this is the capabilities that we have that humans currently do not have, or at least people employed by Amazon don't have. We as robots can say, actually, we can't pick this item. And that's mainly because we have very limited capabilities at this point in time, right? You expect a human to pick almost everything. But at this point where we are in our development phase, we are not able to pick everything. But we need to understand, and it goes back to like that argument that I made before, we need to know when we can't do things, because letting the fulfillment center and the operators know that we can't do things is something they can plan around for. And it's better to do it this way rather than like just saying, well, actually, I'll give it a go and let's see if I can do it. Oops, I can't do it. And then, other things might happen. Things might get delayed, or we might pick things for a customer that are wrong. And so we want to avoid that. But it's actually in itself a non-trivial idea to like say what is the pickability. And there's like a bit of a flow chart here on how that works. I guess I'm slowly running out of time. So let me just try to conclude here with like 2 more slides. The key metrics that we care at Amazon and that our customers and our operators, so like for me as Amazon Robotics, my customer is the fulfillment center and the managers of the fulfillment centers, and their customers are you guys and everybody who's ordering from Amazon. So we all care about the end outcome, which is like getting your order to you in the right way. But in between, we want to make sure that we hit the right targets for particularly this deployment of robotic systems, and tying that big back in with the academic metrics, right? Like most of these things we hadn't in our academic metric. We had something that is maybe along the lines of an eligibility, but usually more a success rate. And we had something in some of the papers that would tell us what is our, in this case, UPH, units per hour. I think in academia we call it MPPH, mean picks per hour, but it's a metric about the throughput. Other things that Amazon cares about is the fullness, like how densely packed things are, how few items we're damaging. Amnesty is, as I mentioned before, when items fall on the floor. So this is called an amnesty within Amazon. Or particularly doesn't happen with humans that often, but it does happen that you accidentally pick the wrong item if they're particularly close and appear very close to each other. But it happens for a robot very often that you might accidentally start dragging multiple items. And that's because it's really hard to understand whether once you start dragging out one item, you have multiple items coming along. And so we want to understand and measure that. And that's why this is a key metric for us as well. Okay. Maybe one more slide about tech transfer.
Juxi, I think you have time. Like you can take about 7 minutes or so.
Okay.
If
cool.
you yeah.
It's okay. I'll have 2 more slides and I'm happy to go into questions. I hope there's some questions. Cool. Otherwise, I keep talking. But yeah, thanks for that. So I guess the different viewpoints, like in all of these 3 roles, like as an academic, in a startup and an industry, to some extent, we claimed that this system is able to pick everything, right? Like, I think it was literally in one of the lines of our papers is like, this robust reactive grasping would allow to pick up anything that we throw in front of it. Obviously, anything had the caveat of like a specific subset of things. When we went to investors and pitched for a startup, obviously we said, this is a robotic system that can pick any item, any fresh produce item. Obviously, it came with caveats. And the same thing here, even with Amazon. I think we are actually much more explicit that we say we can only start with like a small subset of the items, and then we work our way up by applying more scientific research into the product. But actually, I think the common thing is that, and no one cares about the tech feels a bit strong, but actually, what people really care is how you solve the problem. And so everybody, whether it's the customer within Amazon or the customer that we had as a startup, or even like the industry partner that you talk to as an academic, they will have a very specific problem in mind. And your research and your product might only be one way of solving that, right? So very often as academics, we come from the research side of things and work our way left, right? We build a product and then we see which problems it can fix. But industry and people that actually have the problem usually come from the other way, right? Like they have a problem, there's a bunch of products out there, and most of the time they don't even go to research because very often they, care about the product capability and not how it's being done underneath it. Don't get me wrong, it's very important to have the capability and improve on the academic research. And if you can do things differently, that will help the product in specific ways. But I think it's important to understand that, the industry partners or your customers are coming from a quite different mindset, and you need to balance these things. And when they talk about robustness, it is something different than a metric that you have published in your paper. So I just want to highlight that. And in particularly the metrics that sort of I encountered over the last couple of, well, I guess a decade or so, they do differ, and there's a reasons why they differ, but I think it's important to understand that robustness means different things to different people. And it means different things to where you are in this journey from like an algorithm all the way to a product. And yes, in this case, it's going through various different companies and startups. But even if you do that within one organization, you need to be aware that these things shift. Right? So like you might start with something simple of like, how often can I pick up that item? Your stock standard grasp success rate. Or, how accurate can I be in like picking up an item? And maybe how much is my throughput? But like as Lyra and like in industry, other things become more important. Like cost isn't a metric that we care about, obviously. Defects at Amazon. MPPH, as I said before, is mean picks per hour. MPPH per SQM, like per square meter, is a metric of like how much of the floor space are you using with your robotic system. And that becomes more important, particularly when you retrofit. And other things, not particularly to Amazon, but like lots of deployed robotic systems will care about MTTR. mean time to recovery. So if something does go wrong, how long does it take to go back up again? So it's usually a metric around downtime and uptime. Awesome. And with that, let me just jump to that last slide. Feel free to reach out, with questions here. Add me on LinkedIn. Feel free to ask me questions there as well if you don't have time today. This is both the Stow and the Pick system as videos in the background. And yes, I get asked it a lot. And yes, we are hiring. So feel free to ask me questions about that one as well. And with that, happy to take some questions. Thank you.
Hey, great talk, Juxi. Thanks. So does anyone have any questions? Okay, so wait, let's start with Rahul. Rahul, you can let me just read Rahul's question. I don't know if Rahul's online. So he's asked, how does recovery mechanism take place? For example, picking of fresh produce. Is there a rank of choice? If certain item pickup fails, does it go to the next best choice?
Yes, that is a good question. That's actually a great question. There's usually not just one way to solve that, right? And like with algorithms and everything, there might be a trade-off. How we did it in that video that I showed. Actually, let me go back to that one. At Lyra, what we were trying to do is, let's see, where was the? So, in particularly in this case, let's touch on this one in particular. We have a metric that will tell us what is a good grasp point. Doesn't matter what that is. In this case, it's a deep learned one, but it doesn't matter. So it basically gives you a map of where good grasp points are in the world. And so basically what we did here is basically an inhibition of that activation if we just tried it, right? So like basically there's a temporal aspect to it. If we, if there's a new 20 milliseconds afterwards, a new image comes in and we do the same optimization again, and we get a different set of grasp points. If we had just tried one, if we performed an action, the neighborhood of where we just tried to pick up would get an inhibition, as in like their activation function or like their fitness score or whatever you want to call it, is reduced. And so therefore, we would try to pick up something else, right? And so that's the way that we particularly in this case dealt with it, where we knew that we are in a semi-static environment, and the semi part is critical here. Like it's static for the time, or we can not guarantee it, but we assume that it's static for the time between taking the image and trying to perform the action. But we also will most certainly not be able to, if we take another image like 20, 40 milliseconds later, get the same output. And so we actually leverage that aspect by saying, well, if you can't do it, we'll just take another image, and we force like a variability of it with that inhibition of the previous grasp point. And so the next one will pick a different best choice. So we don't actually have a ranking from before. We always do that on the fly, but the temporal aspect will inhibit certain geometric areas with the image frame. I hope that sort of answered that, Rahul.
Okay. Okay, so the next question is from Karthik Nambiar. Karthik, go ahead.
Hi, thank you. Am I audible?
Yeah.
Yeah, thank you for the wonderful talk. I had 3 questions basically. One was, how do you solve the sim to real challenge? Whether it's there or do you use simulations to your tech? Second one is, what are your thoughts on VLAs, vision language action models in real life applications? And third was, is there any better way than manipulation, or manipulation is basically mimicking what humans do, or is there any better system to interact with objects or better automation systems than other than manipulations that can tackle these sort of problems? Thank you.
No, those are all great questions. I'll start backwards, and if I forget what the previous question was, I'm already sorry for it. But like manipulation, particularly in the case that we do here in the Lyra videos, but also at Amazon, we don't have humanoid hands, right? I think they are probably not at a level where it makes sense to deploy some of these systems. Although if you go to robotics conference, you'll find new hands all the time. So I feel manipulation, for me, yes, mano, like from Latin, means hand, and that's the same that we use for human hands. But I don't think manipulation in robotics requires a human-like hand. I think there's lots of different ways of dealing with it. In terms of automation, yes, you can do a lot of things with automation. Like you can do flippers and like gating and like fancy mechanical sorting systems to get from A to B. You can Google it and find lots of different videos of like how we solved, like we as human race for like thousands of years, some of these things with pure mechanical solution, and they're very fascinating. But I think there's a limit to what you can do, and I think you require some sort of manipulation, but I don't think you require fingers. Like vacuum suction cup is a very robust industrial solution to that. I'm skipping the VLA question for now. What was your first question? Sorry.
How do you solve sim to real challenges?
Sim to real. Yes. That's an excellent question. So in different parts of my career, there's different ways that we solve the sim to real gap. I think generally you should be smart about what you simulate, right? So I think having the right choice of what your simulator simulates and doesn't simulate, and then dealing with the outfall of that, I think is critical. So in this scenario here, let's see if the video actually, I can stop it at the right thing. So one of the things that we did here is we focused on something where the sim to real gap is not as bad as purely on a computer vision side, and we focused on depth. Because the depth image we can simulate relatively nicely, we can even put some noise on it. But actually, the transfer of the depth images is significantly easier than an RGB image. So this is one way that we solved the sim to real, or that we closed the sim to real gap, so the transfer was a lot easier. I don't think we'll always get to the point where there's no sim to real gap. I think you just have to live with it. But I think smart choices about the simulator and what your problem space is will make it a lot easier to solve the sim to real gap. And now tying that in with VLA, I think VLA are an excellent, exciting technology. I think they're early stage, and I think it's important that we still perform a lot of academic research on them. I know there's a bunch of startups that are trying to solve interesting problems with them. I don't think we have yet figured out what the best way of leveraging VLAs is, right? So about 15 years ago, convolutional neural networks came on, and everybody was like, cool, how we can use that for robotics? And everybody was like, I don't know, throw a bunch of data at it and see what happens. And I think over a couple of years, we figured out, well, actually what the really core of a CNN is, it's a really nice feature extractor. It gives us really cool, robust data-driven features that we can work with. I think we haven't found out what the VLA equivalent is, what the VLA gives us, but I think it will be a tool going forward that we will have used. And more broadly, I'm not sure what language particularly will bring to the table, but I think that's more a philosophical question. And we can discuss this longer, but I also know there's a bunch of other questions up there. So I think personally very excited about it. I don't see it happening, particularly on Amazon scale, anytime soon. I think good old-fashioned engineering can get you a long way before we need to apply a VLA to things.
Okay.
Thank you.
Okay, so there was a question in the text box which I think I should ask because it probably came before some of the hands were raised. So this is from Usman Mohammed. So how do you sync motion control and vision perception? I mean, is it with any online adaptation or pre-programmed?
It sounds like a simple question, but there's lots of subtlety to it. So I think it's a great question. At Lyra, for example, we used something inspired by visual servoing where you have a very closed loop between perception and motion control, particularly of the robotic system, particularly of the joints controller that you run on a stock standard industrial robotics controller. At Amazon, we have a slight different problem where the syncing is not so much between the perception and the motion. It's more so between the different robots' motion at the same time and or perception things that are happening in parallel. And so that's a slightly harder problem. And you can get a long way again by pre-programming these motions and like having enough gaps in between. But very soon you'll realize that it's good to have something that is more online adaptive, I guess, in your wording here, where you have full, as much as you can, at least full state information between the different robotic systems. So you do, forward kinematics that would stop you from doing stupid things like crashing into each other, right? So there's a lot of subtlety in there. I don't think there's one answer to that. It really depends on your problem. Like you can get, and automation companies have done this for like probably 50 years. You can get a long way with pre-programmed motion, right? But in some cases, you do require something that's a bit more synced, and particularly if you do visual-based grasping and visual servoing and similar technologies where you have features, visual features within your control loop are probably a nice way to deal with some of that.
Okay. All right. Okay, so the next question, so this is a raised hand. Sobia Shafi, do you want to ask?
Yes, am I audible?
Yeah, you're audible.
Okay. Thank you for the interesting talk. I have two questions. My first question is, what's the best way to teach some task to the robot? Is it passive observation or kinesthetic teaching or teleoperation? And then my second question is, in this case, in Amazon, is it only vision input which is given to the robot, or do we have some force sensors as well?
No, thanks for those questions. And both are actually excellent questions. So yes, we do use other sensors. We have force torque sensors on the UR robots. We also have proximity sensors. Don't know if I have a picture of them, but we have on that hook, we actually have a proximity sensor, and that's there. So we actually, when we make that motion, don't run into the top of the fabric pod, right? So that's there's some variability, and you can see here where it actually partly runs in there. So we have a proximity sensor on there, and we have proprioception, right? We have the joint positions on there as well of the robotic system. And ideally, you want to cover as much as possible with your sensing, particularly at the early stages. And maybe that's slightly off topic to your actual question, but usually at a very early stage of some of these products, you probably put way too much sensors on it, just because you think you might use it. And then you realize that some sensors are not needed, or you want to replace them with something better, right? And so vision is a very powerful sense because it provides you a lot of information, and you might later on be able to remove other sensors because you can do that from vision. I think that's one of the powerful things about vision. About the first question, I know that a lot of people are doing behavior cloning, teleop, data collection, particularly for humanoid robots, which I guess is where some of that coming from. For us, there's no point of actually learning any of these things, because I think what we still haven't figured out, and that's maybe also a comment about the VLA before, is how do we extrapolate, right? I think interpolation between human teleoperations is something that I think we've shown that it works for some really interesting complex tasks of laundry folding, cable insertion, a bunch of really cool, bimanual tasks that you see robots do. But actually, the motion here is not, well, it's both not complicated and very specific, right? So if you look at some of the extraction videos from that video here, the extraction motion highly depends on the scene that you see. And so even if you do 1 million teleoperations, you might not be able to capture enough of that space to actually perform, for me, behavior cloning, it gives you like a funnel of trajectories that you can sort of stay within the bounds of that. And then, if you go outside of those bounds, you can come back to that. I think in these scenarios, we don't have a funnel. They're so different to start with, and all that's sort of the same is like we know roughly where the endpoint is, but everything else is quite different. So for us, heuristics are a very good starting point, and then RL, like reinforcement learning here, in simulation, particularly if you can do the transfer, is what we chose because it allows us to extrapolate to previously unseen scenarios really well. And we do have like a combinatorial problem here, as in like if there's 20 to 30 items in the bin in lots of different configuration, you have millions of items, potentially hundreds of millions of items. That state explosion of what can actually happen is somewhat tricky. So, and I feel that is maybe a bit of a gap also in the whole humanoids robotics one. Like, I think it's fine to seed your trajectories with like human examples, particularly if you have a higher degree of freedom robotic system. But I think we sometimes overfit to human trajectories, and I don't think that's necessarily always the right thing. I hope that answered the question. I think it was maybe slightly evading, but I hope it was still useful.
Yeah, thank you.
Okay. All right. I think, guys, we're probably close to the end of our time, but okay. So we'll let so Dirkesh, one question for you, Satwik, one for you, and then we have two questions in the chat. So Dirkesh, go ahead. I'll then follow up with questions from the chat, and then Satwik, it's your turn.
Hey, thank you so much. Hey, Juxi, wonderful talk. Thank you so much. I have a control-related question. So you talked about occlusion in the presentation. Inside the bin, when an object is so occluded that the robot can't really see where the center of mass lies. Like how do you compute like how much force needs to be used for suction, and then like removing that? Like how is that computed?
Yeah.
My follow-up to that was also like, I mean, with actual manipulation, like how do you ensure that the force is not so excessive that you damage the product, right? Essentially, two questions. Sorry about that.
Yeah. No, all good. You're a bit low on volume, so let me just rephrase just to understand what I understood the correct question here. So it's basically about forces in the bin and how do you make sure that you don't have damages, both in terms of like, when we extract the item, but when we also,
Yes,
I
that's
guess,
correct.
pick it
And
up.
also, like, how do you compute like how much force to use when like the center of mass is not really visible and there's so much occlusion that it's hidden behind multiple other packages, right?
Yes, absolutely. So it turns out you don't actually have to be super complicated about these things. And that's the same thing at Lyra as we do with Amazon. Vacuum suction is actually really a well understood industrial problem. And really the only thing that we had seen at Lyra was actually giving bruises to the produce if we suck too hard on our produce, or partly ripping things off when we are in the Amazon scenario. So basically, you actually can do this by just slowly increasing the pressure that you actually apply and having some means, and usually you just put like a flow meter or something like this in your pipes, so once you have a seal. And particularly for the Amazon scenario, anytime you have a seal, that's good enough because we don't need to like hold it for a long time and swing it around and make sure that a lot of dynamics are involved. We actually just drag it out, right? So actually we don't even have to fight gravity for too long because we just, as soon as gravity actually acts on the item, we can actually let go and let it fall onto a conveyor belt. So I think that's one of the smart choices that they made with the system. You don't actually have to deal too much with that, not that you don't know where the center of mass is, that you don't know exactly the weight. We do have some information about it beforehand from Amazon's databases that you can see on the webpage as well when you order things. But it turns out vacuum suction cups and flow meters is a very good combination to have very high robustness by just having a very simple controller around it. And I think that's really one of the core things why people still use vacuum suction cups over like anything with a hand or fingers or tweezers or other things, because it's so much easier to integrate and implement reliably and robustly. Actually, I think one of the questions in the chat was there similarly about like gently pushing surrounding objects out of the way. And so I think the gently pushing things out of the way is slightly different, but like knowing when we actually run into items, again, we can use both force torque sensors and other things that we have, but also we can use the vacuum flow detection to understand whether our seal is breaking. So it is a very good reasoning method for us to understand whether we were successful or not, is both can we create a good seal, and is the seal constantly happening on the item until we extract it. Now, there's obviously a caveat, like you can't do this if an item like, you have a sieve or a colander or something like this, where there's just a bunch of holes and you can't really suck that. But luckily, there's not too many items like that. But it's clearly a limitation of our system. But it's one that I think is a very well understood and decent pragmatic trade-off that we chose. There's actually one more thing. So like, I'm just going to add like half a sentence, sorry. When like our system team that stows the item, they have a significantly harder problem because sometimes they actually need to make space, right? Like they need to squish everything in so they can actually stick the book in. And that is a significantly harder problem. And unfortunately, I can't talk too much about this one, mainly because I don't know what to do exactly under the hood. But they've written some papers about it. And if you Google Vulcan stow, you'll find some information about what you do. But for them, the dynamics of that information is even more important than it is for us.
Got it. Thank you so much.
Okay. Great, thanks. So, Juxi, we have one question in the text. This is transferring learned policies from simulation to real life comes with its challenges. How do you tackle those? And what perturbations do you account for while training? So there's that.
Yep. That's a quick one to answer. Like I think I mentioned some of the sim to real before, like choosing the right things to simulate, and then that makes the simulation closer to your reality and therefore easier to translate. Well, it does help if you have large compute resources because we can put a lot of noise on it and run these simulations a few times. So how do we tackle that at Amazon? By running a lot of these simulations in parallel. And I think the video is still playing in the background, but you can see it somewhere, I guess, here in the video, where all of a sudden you see one of these Muchoka simulations running, but then you actually, I'm sorry, a bit later, you'll see that we can actually run a lot of them in parallel, right? And that's one of the advantages that you have at Amazon. You have like a large amount of Amazon cloud compute, and that allows us to run a lot of these things with perturbations. And usually the noise level comes from position error as well as depth error in this particular case. So again, understanding what your simulation is and where your gap is coming from, kind of like when we did a long time ago sim to real transfer with like vision policies, for like computer games, like the whole Atari thing and other things that DeepMind did. They understood that a lot of the noise comes from colors being, perceived similar by humans, but the numbers that you get out of a sensor vary quite a bit. So like, you do some fancy in painting or change of color to get that out. Again, understanding what the core differences are and how you choose them. And again, I think for us, that makes a lot of sense. And then you can model the noise of your depth sensor, particularly if you have like millions of images of your depth sensor, you can actually model the noise relatively well. But then also like still playing around with like running a bunch of these things in parallel so you can actually be robust to these changes because both interpolation and extrapolation can be done. That's how we deal with that. And that works maybe surprisingly well, but it works relatively well.
Okay, and there's one question. This will probably be the last one for the evening. This is from Satvik Kumar Sahu. Satvik, go ahead.
Hi.
Hi.
So thank you for the nice talk, sir. There have been a lot of developments in world models and MPCs. So you could basically tell the consequences of your actions in the world, and they also solve an optimization problem during deployment to perform the actions. And this could possibly be an answer to the question of how to know whether or not your robot can perform a particular task. But what are the problems that could be faced in the real world if you deploy these in Amazon Robotics?
Yeah, so world models is clearly a hot topic, and absolutely the reasons that you mentioned is I think is why people are excited about it. We have people within Amazon Robotics, not within our group, but like people who work very closely. And if you were at ICRA this year, or like even if you just Google ICRA 2026, there's some Amazon papers about some of the world models that they are using and developing. In terms of deploying them, which I think was the second part of your question, it's kind of like a chicken and the egg problem, right? So if you had a really good world model, that's fine. But like, where do you get the data from so the world model actually understands, the physics outcome? And usually that means you have to have some previous data that you can bootstrap that information from. And so the approach at Amazon, and I wish I had that slide from one of my colleagues in the Stowe team. It's a brilliant slide. I will have to steal it. So you have to imagine that for a second. But like, so it basically was plotting like the total amount of items, in this case, parcels sorted, over time, and like from 0 to 1 billion in production. And basically the first 50, 60,000 was a heuristic with some human annotation of like outcomes and issues about, in this case, it was parcels that were not actually placed on a conveyor belt, but fell off. And that's a big thing, right? Because the customer doesn't get the order. So understanding when that was happening was so much more important for them to like increase the percentage of like, throughput or quality, because it would allow the system to run long in operations and people in the warehouse to be confident that, customers will still get the orders. And then eventually they swapped to a machine learned approach. And now they have published this world model, which works on a lot of this data over those billion of sortations that would actually help you with some of the exactly, let's say, physics predictions, outcome prediction that you want, right? But it needs a lot of this data. So I think the approach that we at Amazon, at least in some of the teams in Amazon, are doing is like, how can we bootstrap these world models on the specific problems that we have? We don't need a world model that predicts, pedestrians crossing or chickens walking in front of a car or something like this, right? We really only care about, particularly in our case, the manipulation and what happens to the items that we poke and pull and lift. So I think it's an easier one, but it still requires a bunch of data. And I think that's for us, at least internal, the way to go. And Whether they are using that world model in production, I can't answer. I don't think they currently do, but it's recently been published, so it usually takes a bit of time. But I think it's a natural transition and evolution in that direction. But it's not the first thing that we would put and require from a product, right? And maybe at some point in the future they'll be so good that we can just have that as a standard part of a robotic system that tells you exactly what is going wrong. That would be great. I would love that world model, but I'm dubious whether we're going to get there in the next year or two.
Thank you.
Great. Okay. All right. So let's thank Juxi. Juxi, great talk, and thanks a lot for staying back. I mean, we've had probably one of our longest Q&A sessions. So thank you very much for this.
Thanks, Juxi.
No.
Thanks, Juxi. That was a great talk.
Thank you for all the questions, and thanks for the participation. Happy to answer these. And yeah, feel free to, if you have other questions, feel free to reach out via LinkedIn or my email address, and happy to answer that as well.
Great. Okay. Thank you, everyone.
Thanks, Juxi.
Yeah. Thanks.